Hello, we're going to talk today about dot product and cross product. In physics, it is very important to know when things are parallel forces motion and when things are perpendicular. Um, the more parallel the force with the motion, the more efficient the system is. And with torque, the more perpendicular we are to the vector that we are trying to turn, again, the more efficient we are. So it is very important to measure parallel forces and perpendicular forces. The dot product and the cross product do that quite well. The cross product adds more to it also. So we got vectors v and w. If I don't say anything else, I'm going to assume that v is a vector with coordinates a, b, c, and w is a vector with coordinates l, m, n, with a, b, c, l, m, n being real numbers. So a, b, c, real numbers, and so are l, m, n. Okay, let's draw a quick table. If we have u dot w, and we get 0, then we have perpendicular vectors. Then v, u, and w are perpendicular. So this is the symbol we use for perpendicular. Or orthogonal. Yep. If this dot product is maximum, then the two are parallel. The two vectors are parallel. So this is the symbol we use for parallel. On the other hand, if u crossed w is 0, then we have parallel vectors. And if it is maximum in its magnitude, okay, so there's something I have not told you, and that is this 0 is a scalar. The dot product will always be a scalar, the result of the dot product. The result of a cross product is a vector. So this is the vector 0, to emphasize, while this is the scalar 0. After this page, we're going to assume that the context will tell us whether we have a scalar 0 versus a vector 0. And if the magnitude is maximum, so I'm going to put maximum, but by that we mean the magnitude. Actually, this dot product could be negative, so we should also use here absolute value. If the absolute value is maximum, then we got parallel. And if the cross product is maximum, the magnitude rather is maximum, then we have perpendicular vectors. So the dot product and the cross product are very useful to tell us whether two vectors rather are parallel or perpendicular. Not only that, they can tell us a measure of how much they are not one or the other. There are more properties of the cross product. The cross product gives us a special kind of a vector. The dot product does not gives us a vector, it gives us a number, a scalar, which contains some important information. It is a good idea to compare one versus the other as we study those two operations. It is good to contrast one versus the other. So I'm going to emphasize that u dot w, the result of this is a scalar, That means a real number in this case. U cross w is a vector, which in this case is going to be part of r cubed. In fact, let me start with a new sheet. The dot product can be performed with any dimension. So let's contrast again one versus the other. So dot product happens or may happen at any dimension. In contrast, the cross product may only happen in 3D. We cannot do the cross product in any other space, but the R3. So let's start with the definitions rather, plural definitions. If you have three-dimensional vectors v, w, and we multiplying with the dot product, we will end up with a comma b comma c dotted with l, m, n. And the way we obtain the output of this product is by multiplying the first coordinate of the first vector with the first coordinate of the second vector, a l, that's going to be a real number, add to that bm, add to that cn. Cn. At first sight, if we're not paying close attention to this, it may look like we end up with three parts, which makes it look a little bit like a vector. But of course, this is not a vector. These are not commas. We're actually adding those three numbers. Let me give you some. Well, before I give you more examples, though, I wanted to show you that if we have other vectors that are shorter, say, A with coordinates A1, A2, so that is a two-dimensional vector, and B, B1, B2, then the dot product of A and B will be A1, B1 plus A2, B2. So we just multiply the corresponding coordinates, components of the vector, add those products, and that's the end of it. If we have C equaling C1, C2, C3, C4, and then D, and D equals D1, D2, D3, D4, then I should probably make a full sentence out of those two statements. So I'm going to add if, and then the dot product of C and D will be C1 D1 plus C2 D2 plus C3 D3 plus C4 D4. And you can do that for any number of dimensions. All right, so now let's look at some simple examples. So examples, say we want to multiply the vector 0, 1, 0 with the vector 5, 6, 7, the dot product of those two vectors. So what we do is multiply the first coordinates. 0 times 5 is 5. Rather, 0 times 5 is 0, plus 1 times 6 is 6, plus 0 times 7 is 0, and then we add those numbers together and we end up with 6. Yeah. So multiplying by this vector, which is the j vector, is the same thing as projecting on the y-axis. If we multiply 5, 6, 7 with 1, 1, 0, 5, 6, 7, then we don't end up with a projection. We end up with 5 and 6 added together. So 5, because 1 times 5 is 5, plus 1 times 6 is 6, and then 0 times 7 is 0. And then we add all of that together and we end up with 11. So we do end up with a projection only when we multiply with I, j, or k. Then we pick up the corresponding coordinate of the other vector. Yep. Something nice about this is that it is easier to get a grip on whether two vectors are orthogonal or not, or perpendicular or not. Orthogonal and perpendicular are going to be synonymous. So as a new example, okay, so find an orthogonal vector to the risk of making this harder than it has to be. I'm going to use 5, 6, 7. So let's say I want to find something that is orthogonal. I want to make sure that I get a dot product that gives us 0. So for instance, we can, so again, we want to find a vector. So the answer is going to be a vector with 3 coordinates. And when we multiply 5 times the first coordinate, 6 with the second coordinate, and 7 with the third coordinate, and add those products together, we should end up with 0. So for instance, we can crisscross the 5 and the 6, 6, 5. So 5 times 6 is 30. 6 times 5 is 30 as well. So to undo each other, I have to make one of them negative. So for instance, this could be negative. And if we set the third coordinate to be 0 there, we got 0. So 5 times 6 is 30. 6 times negative 5 is negative 30. When we add those two together, we get 0, plus 7 times 0 is 0. So there's one solution. There's many solutions. So this is the answer number 1. We can have an answer number 2. For instance, what if we put the negative on the 6 instead? Negative 6, 5, 0 is also perpendicular to that. And somebody could say, wait a minute, what if we What if we use 5 and 7 and not the 6? Sure. 5, 0. Oh, there is a mistake here. There's white out, but it's faster just to scratch and put 7, comma, 0, and then -5. Yep, that will be perpendicular, orthogonal to this vector. 5 times 7 is 35. 6 times 0 is 0, so 35 plus 0 is still 35. 7 times negative 35, I'm sorry, 7 times -5 is -35. We already had 35 plus -35, that is going to give us 0. So this is perpendicular. And just as before, we can put the negative on the 7, so -7, 0, 5 is also perpendicular to that vector. There's an infinite number of perpendicular vectors. You can take any of those, and so these are just kind of random. This last one multiplied by 2, and we end up with a perpendicular vector to this one. So we're starting out with this vector, 5, 6, 7, and all of those are perpendicular to that one. Now, we do not know, in fact, it is very unlikely that, it turns out, as I'm looking at this, that, oh, no, they're not perpendicular. I was thinking that perhaps those two are perpendicular, but no, they're not. Why not? Because if we do the dot product of those two, we do not end up with 0. 6 times -6 is going to be a -36, and -5 times 5 is -25, and we end up with a fairly large negative number, not 0. So those two are not perpendicular. So we're generating a whole bunch of vectors, not necessarily perpendicular among themselves, which are definitely perpendicular to the given vector. I interrupted myself here. I was going to multiply this by 2. So -14, 0, 10 will be perpendicular to this one. And you can multiply by any number. You can multiply by 0. Oh, there's one interesting oops, 6 example, or answer number 6. There's an infinite number of answers, and they're not necessarily in any particular order. One solution is 0, 0, 0. So this vector will be, by our definition, we haven't actually defined what perpendicular or orthogonal means, but we could define that two vectors are orthogonal if their dot product is 0, in fact. And that coincides with our geometric notion of perpendicular vectors. Even this one will be considered perpendicular to that one, even though there is no magnitude to this. So we still allow that to be part of the definition of perpendicular vectors. Okay, we're going to talk more about properties, but again, I like to contrast dot product with a cross product. So let's talk about the cross product. So if V is equal to A, B, C, W, L, M, N, then the cross product will be a new vector. And this vector is, the formula for this vector is rather, I would say, complicated at first. We cross multiply B, N, and then cross multiply C, N, subtract those products to obtain just the first coordinate. So just to get the first coordinate, we have to multiply, subtract. We have to do 3 operations just for the very first coordinate. So again, Bn Bn, Cm, and then subtract. So in order to get the first coordinate, we use the last two coordinates of each one of the vectors, original vectors. Let me do the last coordinate of the cross product. We do exactly the same kind of pattern in multiplication. So back here we did Bn, and then we went down the other way. Here we went down diagonally, crossing the B and the N, or multiplying the B and the N, and then crossing the other way. And we're going to do that here also. A with M minus BL. BL. So AM minus BL for the first and the last. For the middle one, we're going to use the extremes, the first and the last coordinate, and the last and the first coordinate, but in the opposite pattern. So let me repeat. When we found this first coordinate of the cross product, we went down initially. So the slope is negative as we do this motion, and then the slope is positive. But when we find the middle term of the cross product, we're going to start with a positive slope, CL minus AN. And that's it. There are many different ways to memorize this. Whatever you use, go for it. Some people like one way, some people like the other way. Some people introduce determinants, which work just as good. Whatever works. There's no one better way than the other. In my opinion, I think if you get an accurate result and the logic is reasonably valid, it doesn't matter which way we do it. If you learned how to do the cross product by another way, and your way is accurate, then go for it. It doesn't make any difference to me. It is a computation. My analogy about computations is if you are adding numbers and then you have to use your fingers to help you remember how much to carry over, I don't see anything wrong with that, personally. Some people think you have to be able to remember that, but I don't see anything wrong with that. So learn how to do the cross product, practice it. In my personal opinion, in my personal experience, it is easier just to remember the motions down and up. I don't even think too much about which one I'm multiplying. It is about a little bit like dialing a telephone number. Oftentimes, in my experience, I don't even remember the numbers. I just remember with the motion of which numbers I need to dial. But now let me talk a little bit about why. Why do we use these formulas? And that is not an easy question to answer. Not to mention there are different levels or ways to answer the question. I'm going to give you one answer, which is not necessarily the best answer, but it works for me. And I'm not trying to be evasive, but the answer that I think works is because it works. So my personal answer, yeah, because it does what we want quite well. Okay, yeah. I don't necessarily think of a deep solution. I don't necessarily think there is a very, very deep reason why the formulas are the way they are. They just happen to work well, so we keep them. Let me give you a quick analogy. I hope it is quick. To me, why using this equation or this formula is a little bit like asking, why do tables have 4 legs? You know, if you have a table, typically it has 4 legs, although there are tables with different configurations, but most tables have 4 legs. And one could ask why? Well, it just works really well. If you have 3 legs, perhaps the table will not be as stable. 2 legs are too few, unless you have a back wall that perhaps supports part of the table, but then that is not really a table. 5 legs may be overdoing it. 6 legs are too many, perhaps. So works is the least that keeps the table reasonably stable for most purposes, and that's why we use 4. There's no deep, in my opinion, reason why we do that. Why do cars have 4 tires instead of 3? Even though there are vehicles with 3 tires or 2 wheels, why do we have 4, not 5, not 6? Again, it happens to work well, and I do not think there is a particularly deep reason why. And in that sense, those formulas do what we want them to do very well. They capture when things are parallel very well. When they're not parallel, these formulas capture how much they are not a parallel. They happen to be in magnitude maximum. The cross product is maximum when the 2 vectors are indeed perpendicular. So the formulas that we're using for the dot product and the cross product capture what we want them to capture quite well. So we use them, we keep them. There are some geometry, perhaps, that we can use to explain it in a little more detail, but I think that adds more detail. I don't think it adds necessarily to the philosophy of why we use those formulas. Let's move on to properties. Properties of the cross product and the dot product. Well, the first thing we want to make sure we understand is the dot product of 2 vectors gives us a scalar, is a scalar, while the cross product of 2 vectors is a vector. So that brings up, we have to be careful when we write things down. For instance, we cannot cross, okay, so as an example, it's not really an example, not everything we write will make sense. If you put V cross W, okay, and well, that's going to be a vector, so that will make sense. Sorry, let me change this example. I meant V dot W, there we go. And we cross it with a 3rd vector, say U. This expression is nonsense. Yeah, is nonsense. Because whenever we cross, whenever we apply the cross product, we have to have 2 vectors. This, well, we're assuming that is a vector. But the dot product gives us a scalar. So we cannot cross a scalar with a vector. And consequently, that is nonsense. So I guess what I'm trying to say is if you have a cross product, you got to make sure that the 2 parts that we're crossing have to be vectors. Must be vectors. Otherwise, things are not going to work. The dot product, same thing. Yep. So let's put a comma or semicolon. Those also have to be vectors. Have to be vectors. So a natural question may be, well, what if is there any way we can combine a scalar with a vector? And the answer is sure. You can have a scalar 7 times the vector 2, 3, 4. In that case, we have scalar multiplication. And we don't put a symbol in between. Yeah, in that case, we have scalar multiplication. So that is the very, very first property. It is crucially important to know what happens, what is the output of multiplying two vectors, because there's different kinds of multiplication. So we have to be very, very careful. We are adding operations to the operations we normally know. The dot product, that product is commutative. Yep. But it is not associative. Yep. But not associative. It doesn't even make sense to have 3 vectors dotting each other. Let's see. If you have the vector v and then multiply with the dot product with w, remember, this is the multiplication of corresponding coordinates, and then we add them together, the products. Well, if you switch around the vectors, that means that we're switching around the coordinates. They're still corresponding, and since multiplication of real numbers is commutative, then we end up with the same answer. Yeah. So that is the same thing as w dot v. But v dot w and then dot it with u. Well, this is almost funny. Usually the way association works is that you can group the elements differently. So w dot u without changing the order. So we still have vwu, vwu, but they're not equal in general. Furthermore, they don't even make sense. They don't even make sense by themselves. Why not? Because we can dot only vectors, but this is not a vector, so we are dotting a scalar with a vector, and that doesn't even make sense. Likewise here, same reasoning. So asking the question doesn't even make sense. Yeah. Asking this question, and that by that what we mean is equal or not equal, doesn't make sense at all. Yeah, we can do that. The cross product is not commutative. So the dot product is commutative. The cross product rather is not commutative, because the cross product relies on that goofy operation of the patterns, diagonal patterns, one way and the other way. if we put the order of the vectors in reverse order, then the patterns are going to be different. The resultant patterns are going to be different. And so we do not generally end up with the same thing. The only time you do end up with the same thing is when you have 0. Otherwise, you end up with the opposite. So the cross product is not commutative. It is sort of skew commutative. Well, let's say it is not commutative. Yep. In fact, there we go. U cross V is equal to the opposite of V cross U. So you don't end up with the same, you end up with the opposite vector in the opposite direction. Let's stop here before we start the next video.